Welcome to our next explanatory video. In this video we're going to apply the formula that we learned in the previous video to braking, so to an object that slows down. And we're also going to learn what the role is of a new term, momentum. Here's where we stopped previous time. F times t equals mass times delta v. Or this could also be written down as F times t equals m times v end minus m times v start. If I apply this to an object that is accelerating from a standstill, that means v start is 0. So the formula becomes a bit easier. F times t equals m times v end. Here's a new situation of an object that is not accelerating, but it is slowing down. So we have an object sliding on a floor, let's say a box. The box has a mass of 50 kilograms and it has a certain speed, and that speed is given 40 meters per second, and there's also a force working on it. Now what you should pay attention to is that the velocity is in a different direction than the force. The force is given 188 newtons, but the force is working to the left and the speed is to the right. This is typical for braking. To reduce the speed, the force needs to be in the other direction. Let's take a look at our formula. This was F times t equals mass times v end minus m times v start. Okay, now in this case the vt graph of this object, which I will sketch now, will look something like this. So v times t, and it will be a line going down because it starts off with a high speed and then goes down to 0 speed. Which means that in this case v end will be 0 meters per second. And that means that our formula becomes simpler. F times t will equal minus m times v start. Now the minus sign might puzzle you, because that will give you negative outcomes. However, there's one thing we should realize. You could think of this box as if it were sliding next to a coordinate system. So if this would be the origin, 0, then this could be 1 and 2 and so forth. And I can also move in the other direction, then it would be minus 1 and minus 2, etc. So this direction is called the positive direction, and that direction is called the negative direction. We've seen it before. So since our force is working in a negative direction, that means the force is a negative number. It's actually minus 188. But if I always have a negative number here and always have a negative number here, I could also simply write the formula down without the minus sign if I fill in a positive number for F. So you can use the formula in this form and you don't need to worry about the minus. Let's start calculating. So we have a force 188. We have a time. Oh no, we don't have a time. That's what we want to calculate. So I'll leave it there. Mass equals 50. V start equals 40. 50 times 40 equals 2000. So I can now find time by bringing the 188 to the other side, which equals 10.6 seconds. Okay, so We're going to use the simulation to see if this gives us the correct time. So let's leave PowerPoint and go to the simulation. Now you see here the crate with 50 kilograms, and I've already given it a speed of 40 meters per second. And as soon as I start play, the box will start sliding and the force will start slowing it down. So we can take a look at the speedometer to see the speed. And I'm also going to use a little timer to be able to measure how long it will take. So, okay, everything seems to be in order. So I need to press 2 buttons at once, which usually won't work, but the deviation will be slight. Okay, 3, 2, 1. Okay, here goes. So the force is working to the left, the speed is still to the right, and the force is therefore slowing down. We get 10 seconds, which matches perfectly with our calculation. So we can therefore conclude that the formula that we learned is perfectly usable with this situation with braking. There's one particular part of this formula that we are using that I want you to pay attention to. That's the right part, which was mass times speed. This part is so important that it's gotten a special name: momentum. Newton called this the amount of motion, and that's a bit of a strange term. We're not used to thinking about motion as something that you can have an amount of. So you could also think of it of how easy it is to, or hard, to make an object slow down. Here's an example. I have 2 cars here with the same mass, but they have different speed. This one has a higher speed. Therefore, its momentum is larger. Momentum is mass times speed. And because of our formula, if you have a high momentum, that will mean that that the time it will take for you to slow down is longer if you use the same force to brake. Therefore, this car will have a larger braking distance. But you can also have a large momentum by having a large mass. A truck and a car which have the same speed but different masses will also have a large difference in braking distance. Because of the large mass, the braking distance of the truck will be much larger. So, momentum tells you something about how easy or difficult it is to brake. To get a bit more of a feeling for this new term, I have 3 objects for you here: a tennis ball, an electron, and Australia. And I've noted down the masses and velocities. What we're going to do is calculate the momenta and put them in order of from little momentum to high momentum. We're starting up with the electron. It has a mass which is very small, 9 times 10 to the power of minus 31, but it has a pretty high speed, 2200 kilometers per second. Now, let's calculate momentum. We multiply those two. We need to convert velocity to meters per second so that we can compare them with the other two. And it's 2200 kilometers, which equals 2,200,000 meters per second. We multiply it by 1,000, which gets us this very small momentum, 1.98 times 10 to the power of minus 24. Also take a look at the unit. The unit is kilograms, which is the unit of mass, and meters per second, which is the unit of speed, which matches up with the formula, mass times speed. Now the tennis ball, mass times velocity. The mass is 0.06. I've simply taken 60 grams and converted it to kilograms, so I divided it by 1,000, and the velocity is already in meters per second. which gives us 0.6 kilograms times meters per second. Then Australia, which moves very slow, 6 centimeters per year, but its mass is huge, 10 to the power of 23 kilograms. So, to convert it, I need to convert centimeters to meters, which I can do by dividing by 100, because there's 100 centimeters in a meter. And I need to calculate the amount of seconds in a year. 365.25 days go in a year. Each day has 24 hours, each hour has 60 minutes, and every minute has 60 seconds. So if I multiply this all and then take 0.06 and divide by it, I get 1.9 times 10 to the power of minus 9 meters per second. So that's roughly 2 billionths of a meter in a second. Then I need to multiply it by the mass, which is already in kilograms. But that is so large that the Australia gets the highest momentum of the three. And this tells you something about how easy it is to stop them. It's very easy to stop electrons. You'll probably do it all the time. A tennis ball, that will hit you and it will hurt, but you can slow it down. But you'll never be able to slow down Australia. Conclusions. Our formula is perfectly usable for braking. If you brake until you stand still, the formula becomes a little easier. F times t equals m times v begin, and you can ignore the minus sign. The right side of the formula, F times v, that is called momentum. So we can also write down the formula like this, m times v equals p, because p stands for momentum and it is given in kilograms times meter per second. The higher your momentum is, the longer it will take to stop. This concludes this video. Thank you for watching and see you all in class.